Thank you very much, Ben, for asking me to give this tutorial on this concept of baryon clearing. So we just had a great talk from Annalisa about essentially quenching of satellites in large-scale cosmological simulations. And I'm going to be talking more about the picture for central galaxies in cosmological simulations. So I want to start with this now somewhat legendary image that we all love to show in our talks. And I'm including it because I think it gives a really good impression of how galaxy formation is a self-regulating process. So you have to have some balance between gas inflows and that gas either forming stars or ending up in gas outflows. And you have to have this happening because otherwise you either overcool and form too many stars or you don't form enough. And something that Crystal Martin touched on in her talk yesterday with her lovely bathtub images is that the CGM is, of course, going to be vital to this self-regulation process. But what I actually want to talk about today is how you can disrupt this self-regulation and the role that the CGM plays in that. And you have to disrupt this self-regulation somehow if you want to produce the quenched galaxy population. And most importantly, if you want to quench galaxies and keep them quenched. So it's not enough to just remove the ISM and remove the fuel for star formation. You also have to stop inflows from the CGM from essentially reigniting star formation in that galaxy. And so the key ingredient for all of this, at least in the simulations I look at, is this hidden ingredient on the right-hand side of this equation, and that's the growth of the supermassive black hole. So how might you go about disrupting this whole self-regulation picture? So in lower mass systems, while they're merrily star forming, you can think of it as the process of getting gas away from the center with stellar, the star formation driven outflows essentially. So in this nice plot by Ben Keller, which is of entropy versus radius, you can imagine stellar feedback essentially inflating high entropy bubbles of gas in the center of the system. And then these can kind of buoyantly float out into the CGM, and then they may either leave altogether or they may radiatively cool back down and replenish the interstellar medium again in a fountain flow. But as you start to form a hot halo in more massive systems, this whole process starts to become much less effective. And it gets to the point, and this was nicely shown by some members of the Eagle team a couple of years ago. Once you start approaching halos of a mass of about 10 to the 12 solar masses, the entropy of the hot halo has reached such a point that it's really higher than the entropy of the outflowing gas driven by star formation feedback. And so suddenly you get this very rapid buildup of gas at the halo center that can't be regulated by stellar outflows anymore. And so all this gas has to do something, and it eventually fuels the rapid growth of the central black hole in the system. And of course, when a black hole grows rapidly, it has to inject AGN feedback. And what we find, and I think this figure from a recent paper by Ben shows nicely, that, I mean, this is an example for Eagle. What you find is that when the black holes grow rapidly in these systems that have reached this critical point, the overall content of the CGM decreases in response to this rapid injection of AGN feedback. And so this is what I'm terming baryon clearing. I don't have a better name for it yet, but really I'm talking about the clearing out of the content of the CGM itself by AGN feedback. And this is something that is seen across many of the kind of flagship large-scale simulations of the day. So these are figures from Eagle, from Illustris TNG, Simba, Horizon AGN, and they all show roughly the same thing, which is the content of the CGM, FCGM, versus halo mass. And what we see at this critical halo mass scale of about 10 to the 12.5 solar masses is that there is the gas content of the CGM of central galaxies is severely suppressed relative to the cosmic average. And so what's doing this damage here is the integrated growth of the black hole. So it's the amount of energy that's been efficiently coupled to the CGM over the system's lifetime. And this is quite nicely wrapped up in the black hole mass as a parameter, which is the coloring of these upper figures here from Eagle and TNG. And you can see that at this kind of mass scale here, the systems with the most massive black holes in at a fixed mass, these red points or redder points here in TNG, are those which host the most gas-poor CGM, essentially. So this is what we're calling baryon clearing. And it's actually something that seems to be required in these simulations to produce the quenched galaxy population. So yes, what I just said, so this baryon clearing process does appear to be facilitating quenching, and this is where we get down to this whole theme that we have this week of how the CGM impacts galaxy evolution. So this is the same kind of figure I was showing in the previous slide of the gas content of the CGM versus halo mass. But now I'm coloring essentially by the specific star formation rates of the galaxies at the centers of these halos. And what you can see very clearly in both Eagle and TNG is that the most gas-poor systems, which have the most overmassive black holes, are the ones that almost universally host quenched or very low star-forming galaxies, whereas gas-rich halos tend to host actively star-forming galaxies. So this is quite complementary to the sort of general results from all the different simulations. So there's a nice figure from Abuzi et al. That kind of wraps this up. If you look at black hole mass versus stellar mass and color it by the specific star formation rate of the galaxy, you see that the systems with the most overmassive black holes are almost always quenched across many different simulations. And this is also supported by some observations. So, of course, black hole masses are very difficult to dynamically determine. There are only about 100 or so systems for which there are dynamically measured black hole masses. And this work from Brian Terrazas really clearly shows that the systems that have the most overmassive black holes are the ones that tend to be quenched. And so the reason that this happens is that this whole process of baryon clearing is a preventative process. So as well as just ejecting the material from the galaxy itself and from the halo itself, you're also preventing what's left in the CGM from cooling and fueling star formation in the central galaxy. And we can see this really nicely in simulations like Eagle and TNG. If we look at the specific star formation rate as a function of halo mass, we can see that all these quenched systems at the bottom here are those which have particularly long CGM cooling times, which is what the coloring represents here. And recent work from the TNG team, from Zinger et al., showed that this is a stronger effect at smaller radius, essentially. So the inner CGM is more strongly affected in terms of this whole prevention of cooling. So if this is just entropy versus specific star formation rate, and you can see that for the most quenched galaxies, the CGM entropy is higher, and that this is a stronger slope here for the inner CGM and for the gas right near the central galaxy. So by clearing out your CGM, you're essentially halting the replenishment of your ISM. And there's a nice complementary idea here from Mark Voigt's recent paper, in that if you reduce the pressure of the CGM, you allow residual star formation driven feedback to just sweep out what's left of the interstellar medium. So that's a nice complementary idea. So all this is about connecting quenching to the properties of the CGM through AGN feedback. But if you remember from towards the beginning of the talk, I said that this tends to happen at a critical halo mass. So one might then ask, why is there such a diversity at fixed halo mass? Why don't you just reach this critical point where you formed a hot halo and clear out your CGM? So this is where we can really get down to the origin of this process, and maybe even the origin of the quenching of central galaxies, really. And what I want to convince you of over the next few minutes is that this is the result of differences in the intrinsic properties of the dark matter halo itself, most specifically in its assembly history, which correlates very strongly with how concentrated or tightly bound the halo is. And this is something that's just purely set by cosmology, by the initial conditions of the universe. Okay, so I could show you this using correlations in large-scale volumes like I have been doing so far, but actually a much more satisfying and beautiful way of showing this is by doing a more controlled galaxy formation experiment. And so we can do this using this genetic modification technique that was pioneered at UCL. And what it allows us to do is essentially take a patient zero galaxy, so to speak, an organic galaxy, which is a star-forming disk in Eagle. And so here's the halo mass accretion history of such a galaxy. And what we can do is essentially turn the knobs on galaxy formation, so to speak. We make small changes to the initial conditions of the simulation, such that this system either forms earlier or later. And so we end up with the same final halo mass, and it's the same system in the same large-scale environment, but it collapses at earlier or later times. So we get a nice controlled experiment here. And it turns out the impact of changing the assembly history of the halo is really dramatic. So if we take a look at how the black hole grows with time in each of these systems, we find that the earlier assembling case here, and I'll talk about what the shading is in a sec, the earlier assembling case here not only forms its black hole earlier because it forms its hot halo earlier, but it forms a more massive black hole as well. And similarly, if you dial the assembly to later times, you form a less massive black hole. And this happens because more earlier assembling things are more tightly concentrated. And this makes this whole process of self-regulating the formation of the galaxy much less efficient. And the black hole has to inject more energy into this more tightly bound system to compensate, essentially. So you end up with a more massive black hole and the injection of more energy and feedback. So the shading here is that there's actually 9 realizations of each of these histories. And we do this because the feedback in Eagle is stochastic. So you just need to, if you're looking at one system, you have to resimulate it a bunch of times to get the real answer, essentially. Okay, so what happens to the system? So there's a lot of plots here, but I'll just give you the highlights. So this earlier assembling system, which has formed a more massive black hole, ejects more of its CGM than the organic galaxy. So you get this really clear difference in their final CGM content just by dialing back and forward the assembly history. And the effects on the central galaxy are just as dramatic. So because of this preventative effect of baryon clearing, we find that while the organic galaxy is nice and merrily star-forming at the present day, almost every realization, so there's some stochasticity here, but almost every realization of the earlier assembling system that's been more strongly cleared of its baryons is quenched. And so here are some pictures of the final galaxies that you get, and you can see that we've taken this star-forming disk and turned it into a quenched elliptical just by dialing up and down this baryon clearing process. And so all these kind of trends also hold true in large volume simulations. So I think there's something really profound here, that you can connect the properties of galaxies to the really intrinsic, pure properties of the halo itself, just through this interaction between feedback and the CGM. So I'm going to turn my thoughts to something more observational now in the last few minutes, which I hopefully have, and just talk about, yeah, what was I going to say? Yes, so I'm really pleased to say that these ideas of ejecting the CGM potentially being involved in quenching are picking up some speed within the quenching community itself. So just a couple of headline results from these teams. So this paper, Bluck et al., they find actually that the best predictor of whether a galaxy in SDSS manga is quenched is the velocity dispersion at the center of the galaxy itself, which of course correlates wonderfully with the black hole mass. So more so than halo mass, stellar mass, any other parameter, they find that it's the velocity dispersion that is the best indicator of quenching. And so similarly, I actually just 2 hours ago was listening to a talk by Sandy Faber about this paper. So this paper by Zhu Chen, they build this toy model for quenching that requires that the black hole is effectively coupled 4 times the CGM binding energy to its surroundings in order to quench galaxies. And they find that this toy model very nicely and cleanly separates star-forming and quenched galaxies in the candles fields. So these ideas of clearing the CGM are really picking up some speed. So now just in the last few minutes, I'll talk about ways in which we could go about observing this. So I'm slightly out of my wheelhouse here, so I would love to hear what the real observers think about this afterwards. But yeah, just to start with absorption, which of course we all love to do. So Ben showed in a paper that we did last year that you can use the covering fractions of absorbers such as carbon-4 as a nice proxy for the CGM mass fraction. And in Eagle, we find that there's a really nice anti-correlation in a narrow halo mass window between the black hole mass and the covering fractions of absorbers such as carbon-4. But there are some difficulties in the interpretation of something like this if you were to go and do these observations. So primarily, there's this issue that AGN feedback can actually briefly enrich the CGM with these ions before these ions ultimately become reflective of having evacuated the CGM. So in this plot from Ben, you can see in Eagle that things like carbon-4 and O6, they actually jump up after the growth of the black hole, and then they drop down. And this is something that's also seen in zooms. So this work by Nicole Sanchez shows, again using genetic modification, that the column densities of O6 are actually higher in simulations with black hole feedback than without. So some difficulties in using these absorbers as a proxy for FCGM here. So moving on to emission. As we all know, doing detailed studies using the X-ray luminosity as a proxy for the CGM mass fraction are a bit beyond our reach for Milky Way mass systems at the moment. We kind of are waiting for Athena and Lynx for that. But all of the simulations are kind of predicting quite nicely now that the systems that are actively star forming and haven't cleared their CGM have systematically X-ray bright halos. And this is true in Eagle, in TNG, and in Simba here. So that's one potential route in the future. But something that's more imminently feasible is actually using eRosita observations. So this is, again, I'm really plugging Ben's stuff here, but so this is something we worked on last year. And essentially what you can do is you can use all these wonderful tools like PyXSim and SOX, etc., that John Zihone and his collaborators have developed to make really realistic mock observations, mock eRosita observations in simulations such as Eagle and TNG. And what they show, if you stack them up about the coordinates of star forming or quenched galaxy samples, is that there's a really clear difference between these two in terms of these mock observations. And it turns out that these differences in X-ray surface brightness between highly star forming, so these solid lines, and quenched in these dashed lines should be detectable once eRosita has completed its survey. So that's something that's a more imminently usable proxy for the CGM mass fraction around these systems. So I think I've probably had my time, but I'll just wrap up by returning to this whole idea of connecting the fundamental intrinsic properties of halos to quenching through this baryon clearing, and just kind of reel off this whole connection here using these nice images of those genetically modified galaxies as a guide. So if you form early, you tend to form a more overmassive black hole in your galaxy's center, and this clears your CGM more completely, elevating its cooling time. And so you're much more likely to host a quenched spheroidal galaxy than in a system which forms later. And I think this kind of connection between cosmology and the properties of galaxies is, I don't know, for me, the #1 reason to study the CGM. It's connecting the dots of galaxy formation. And with that, I'll thank you for your time.
Thank you, John. That was great, and it was, you went 20 minutes, so we have 5 minutes for questions, and I will look for hands. Otherwise, oh, okay, here we go. Kirill, how about you go first?
I guess one quick question is, let me lower my hand. Right, so is there, clearly black holes are a good mechanism for explaining the result of the difference in assembly history. But are there other, basically, could it be that, the black holes and the CGM, the differences in the CGM properties, that they are both caused by something, basically that, they're both caused by the differences in assembly history, but not in a directly connected way. Like, it seems like it's it seems like black holes are a good explanation for the connection, but are there other potential mechanisms?
Well, you can very easily test it by simply. Oh, sorry, go on.
For example, if there are differences in the environment of the halo, depending on when it formed, right? Like the sort of regulation idea.
The beauty of the genetic modification thing is that the environment of the halo is identical because it's the same system in the same environment, and all you've done is just tweak the overdensity field right at the start of the simulation, such that the system overall forms in different times. And you can be sure that it's the black hole that's doing the damage, because if you just simply run a simulation where you don't include black hole feedback, all of these lovely trends that we see completely disappear. So in this whole scenario, we're finding, of course, that early assembling systems, they're more tightly bound, but they actually hold on to less stuff. And that's because of the black hole. And so if you take the black hole out, they hold on to more, like you might expect. So it's really the key, this AGN-driven baryon clearing to connecting the dots here.
Okay. Freka, you are next.
I had a question about the X-ray predictions, which I guess Ben led, but I'm asking you. So how do you know for sure that when you find this in observations that it's because there's less mass rather than that the gas that is there, very dense, has been heated by more feedback? Do you see what I mean? So the star formation, putting it, like heating the gas around it, could also elevate the X-ray luminosity.
Yeah, absolutely. Yeah, so I actually spent the first couple of years of my PhD worrying about that question before I turned my thoughts onto this sort of thing. So yeah, absolutely. Stuff that's been recently heated by supernova feedback is going to be very dense, very metal enriched, and it will dominate the X-ray emission around individual systems. And that's a lot of the cause for, if I just wind back, this scatter in Eagle. Like all of these guys that are the most X-ray luminous, almost all of that emission is coming from this feedback heated stuff. So it's not really very representative of the content of the CGM. But I guess you would hope that in a stack, if you were stacking your Rosetta maps up, you would somehow wash out a fair bit of that, of that phenomenon, and ideally get to the real underlying correlation with just using it as a proxy for the content of the CGM. But yeah, that would be a problem that you'd have to think about.
Thanks.
We have 90 seconds left. So Mark, very quick question, and maybe you've finished it in the breakout room. Unmute.
Pardon me. I just wanted to mention, I put in the chat, I think, the black hole mass is actually responding to the central depth of the potential. And so, it's not necessarily just the black hole mass as the primary cause. The depth of the central potential is determined by how early it forms, which then increases the requirement to have a central black hole, which then does the baryon clearing. So this went back to the question about, could there be a common origin that precedes the massive black hole? I think the answer is yes.
Yeah. Yeah, I mean, yeah, you're right. I don't really know how to respond to that other than to say yes, absolutely. I mean, they seem, all of this seems very complementary, and that the overall halo concentration is really what's setting it all. Whether that's the depth of the potential right at the center, which then, of course, determines your black hole's properties.
I think what we should probably say is, let's take it to the breakout room.
Go to the breakout room. All right. And